Okay, so this entire section is really just a review on zeros of polynomials and how to find those zeros and how many might occur. So let's just look at this first question here. How many solutions does x squared equals 16 have? Well, we know that x squared equals 16, then x equals positive 4 or negative 4. So we already know that this has two solutions and that because they're 4 or negative 4, that both of those solutions are real. But if we look at this one, x cubed equals negative 27. Up until now, you would have said that the answer x would equal negative 3. But this actually does have 3 solutions. However, the only real solution is negative 3. So there's one real solution to that equation, and the other 2 are complex numbers, which we learned how to find those complex roots last class. In general, any equation like this, x to a power equaling some integer, has n solutions. Whatever that power is, that's how many solutions it has. However, the question how many are real, there are only ever 0, 1, or 2 real solutions to any equation like that. So at most, we are only going to see 2 real solutions. All the others will be complex. So this is just this review, example 1. How many zeros does p of x have? Again, we can tell that just from that highest degree. So this has 5, although some of them may repeat. So sometimes it doesn't look like they have that many because they're just repeating zeros. And we use the word multiplicity to talk about how many times a zero occurs. So if we look at example 2 here, and we're talking about multiplicity. If we've got x minus 3 as a factor, then we have the 0 x equals 3, and because the exponent of that factor is just 1, it's got a multiplicity of 1. So multiplicity of 1. So again, multiplicity is just the number of times a 0 occurs. Okay, and then the 0, this factor right here would give us the 0x equals negative 1 with a multiplicity of 5, meaning the 0, negative 1 occurs 5 times. And then this factor here gives us the 0, 4, multiplicity 2. And last semester we learned how to graph functions like that, what those would look like based on their multiplicities and their zeros. But we're just kind of reviewing how to find their zeros right now. So in example 3, we have a function. We're told to find the zeros and their multiplicity. So the first thing we would want to do is set it equal to 0 if we're finding the zeros and factor it. So right now we can factor out x squared from every term, which leaves us with x to the second power plus 4 x minus 21 equals 0. And we're going to continue solving this. So I can factor my second group here, what multiplies to negative 21 and adds to positive 4. That would be x plus 7 and x minus 3. So these factors give us the following zeros. We have x equals 0. That comes from x squared equals 0, but because of that 2, we know that this has a multiplicity of 2. We have this factor, which gives us the 0, x equals negative 7, which just has a multiplicity of 1 because of the exponent is 1. And we also have this factor, which gives us a 0 of x equals 3 with multiplicity of 1 as well. Again, this should all be pretty much review, looking back at how to find zeros of polynomials and their multiplicity. Now we're going to be looking at, if I tell you zeros of a polynomial, can you give a possible polynomial that could have given us those zeros? So in example 4, give a polynomial in expanded form, meaning not factored, of degree 3, so the highest degree is 3, that has zeros 2i and negative 8. So the interesting thing here is that we're going to be introducing complex zeros. So if we know that those are the zeros, then we know that our polynomial, we'll call it p of x, has to have the following factors. If 2 is a 0, then x minus 2 is a factor. If I is a 0, then x minus I is a factor. And if negative 8 is a 0, then x plus 8 is a factor. So we just want to write this in expanded form. To do that, I would actually rearrange this so that these two factors were next to each other so that we can do that multiplication a little more easily. So x minus 2 times x plus 8. I'm going to do that first. And you end up with x squared plus 8x minus 2x, so plus 6x, minus 16. And then that's times x minus I. And then we're going to distribute that x minus I as well to everything. Again, if you want to rewrite it, you can. You don't have to. It's still doable. I'm just going to rearrange it so I have my shorter group in the front. And I'm going to distribute. So that would be x cubed plus 6x squared minus 16x minus x squared I minus 6xi plus 16i. So we've got several terms with an I in it. And so let's simplify this. So we've got our final polynomial p of x equals, so I've just got 1x cubed. I'm done with that. I have an x squared term here and here. And so I'm just going to take that x squared, and that's multiplied by 6 minus I x squared. And then I've got 2x terms here and here. So I'm just going to put plus x times negative 16 minus 6i plus 16i. So I've still broken this down into a polynomial based on my cubed term, my x squareds, my x's, and then anything else. What I do want, the most important thing to notice from this example is that I was given a complex zero with an imaginary part, and in turn those factors gave me a polynomial with non-real coefficients. So the coefficient of x squared is 6 minus I. That's not a real coefficient, so that's not considered a real coefficient. So basically what I want you to notice is if you have a non-real 0, you might have non-real coefficients. And we're going to see in 9.6 situations where you will have real coefficients even with non-real zeros. So turn on over to 9.6 and we'll get into that. Okay, so in order to find all of the zeros, including complex zeros of a polynomial, we are going to need to review how to do long division. So if you feel like giving this a shot, I would go ahead and just pause the video and try and do this long division on your own. If you feel like you need the refresher, you can follow along with me, but this will come in handy here in a few more problems because we're going to have to do long division to start simplifying some of these polynomials. So let's do this long division over here to the right because we're going to need a little bit of space. So our divisor is 3x squared minus 2. And our polynomial is 6x to the 4th minus 9x cubed plus 2x squared plus 4x plus 5. Okay, so the first thing we're going to do is ask ourselves, what do I multiply 3x squared by to get 6x to the 4th? And that would be 2x squared to get 6x to the 4th. So I'm going to write that above 2x squared. Then I take 2x squared and I multiply it by both 3x squared to get 6x to the 4th and negative 2. So it would be minus 4x squared. So just make sure you write that underneath the x squared term here. Once you do that, we subtract. So we subtract, what we're subtracting this negative, so really we're adding it. So the x to the 4th term goes away, and we're left with negative 9x cubed plus 6x squared plus 4x plus 5. And we repeat the process. What do I need to multiply 3x squared by to get negative 9x cubed? And that would be negative 3x. And then I take negative 3x again and multiply it by both 3x squared to get negative 9x cubed, and multiply by negative 2 to get positive 6x. So write that under the x term. And then again we subtract, which would make that really adding, and then subtract that. And we end up with 6x squared and 4x minus 6x is negative 2x plus 5. And we are not done yet, because if you remember, we need to continue until this degree, which would typically, this will be our remainder eventually, is less than the degree of our divisor. And it is not. It's the same, so we need to do it one more time. So what do I multiply 3x squared to get 6x squared? That's 2. Take 2, multiply it by both terms, 3x squared to get 6x squared. Multiply by negative 2 to get negative 4. And then I subtract, which is really adding that, and I get negative 2x plus 9. So we're done, and we have this right here, which is our quotient. And this down here is our remainder, r of x. So that's just a brief review on polynomial long division. We will need to use that here in a little bit. Also, something that we should review, to verify that something is a 0, we had a theorem, the remainder theorem, that helped us do that. And it said that, well, first of all, if we want to know that if this is a 0 or not, first of all, it shouldn't have a remainder when we would divide. But if it is a 0, we would just plug it in for x, and we should end up getting 0 as our answer. So to verify that something is 0, you should plug it in and expect to, when you calculate or evaluate, you should expect 0 as a result. So if you plug this into your calculator, you should in fact get that p of 7 equals 0, which would mean 7 is a 0 of the polynomial. So these are just two things to quickly review before we look into solving equations or finding zeros that will give us complex zeros, which we haven't really looked at. We've only been solving equations over the real numbers, and so now we'll see what that looks like over the complex number system. You will need the quadratic formula, so just remember that that's a useful tool, and not to shy away from it if you need it. So solving this equation, x squared plus 1x plus 1, if we were going to try and factor that, we would try and multiply two numbers together that both added to 1 and multiplied to 1. But those two numbers don't exist. So in the real number system, So we have to use the quadratic formula. This is a, b, and c. So negative b would be negative 1 plus or minus the square root of b squared, which is just 1, minus 4 times a, which is 1, times c, which is 1, all over 2a, which is 2 times 1. So let's simplify. We've got negative 1 plus or minus the square root of 1 minus 4, which is negative 3, all over 2. But we also know that the square root of negative 1 is I. So when we write our two zeros for this, if we want both the positive and the negative 1, so the positive 0 would be, this positive 0 would be negative 1. Well, we're going to write our answers in a plus bi form, so I'm going to split up my fraction here. Negative 1/2 plus the square root of 3 times I halves. That's one solution. And we have the negative solution as well, which is negative 1 minus the square root of 3. I'm pulling that square root of negative 1 out in terms of I, and each of those are over 2. So we have these two solutions. These are our only two solutions of that equation. Both are complex numbers, and now they're both written in binomial form. So that's how we'll solve some of these equations that have complex zeros. So let's do one more. We'll do B, solving this equation over the complex numbers. So again, this is something that if we did try to factor, we wouldn't be able to. And if you're not sure, it's always great to just use the quadratic formula because that's just a guaranteed way to find those zeros. So we have x equals negative b, which would be positive 1. Plus or minus the square root of b squared, which would be 1, minus 4 times a times c, all over 2a, which would be 6. So this simplifies to 1 plus or minus the square root of 1 minus 4 times 3 is 12, times 4 is 48. All over 6, so we're looking at 1 plus or minus the square root of negative 47 over 6. So I'm going to rewrite both of my zeros in binomial form. So one of my zeros is the positive version of this. X equals 1 plus the square root of 47I over 6. And the other one is 1 minus the square root of 47I, both of those over 6. Forgot to write these in binomial form. So this is how you write those solutions to a polynomial, or zeros of a polynomial, in binomial form. So there's something really important that I want to point out that you may have noticed or maybe not, but the most important thing when looking at zeros, complex zeros, and polynomials with complex zeros is that if we look at a and b, both of these polynomials, both of those polynomials have all real coefficients, 3, -1, 4, and 1 and 1. So those are all real coefficients. Nothing about those polynomials up front tell us that they're going to have complex zeros. But if you look at their zeros, they're almost identical, except 1 0 is the complex conjugate of the first. Same with part B. We've got 1 6 plus root 47I over 6 and 1 6 minus root 47I over 6. So what happens is if you've got a polynomial with real coefficients and it's got a complex 0, then that zero's complex conjugate also must be a 0 in order to form a polynomial with real coefficients. So So if you looked back at the previous page where we had the zeros on example 4, we were given the zeros 2i and negative 8. Because I is a complex 0 and negative I wasn't, its complex conjugate was not a 0, that produced a polynomial with non-real coefficients. But in these examples, if you've got a polynomial with all real coefficients and you've got a complex 0, then another 0 has to be its complex conjugate. So that's kind of a big tool to help find all the zeros, because if it's got real coefficients, then that polynomial you already know one other missing 0. So the conjugate zeros theorem says if p of x is a polynomial with real coefficients, if the non-real number, so complex number a plus bi, is a 0 of p of x, then its conjugate z bar, which is a minus bi, is also a 0. It's a big deal, and it will help you find all of the zeros of complex numbers. So we will stop there and finish up the last page of 5.6 in class together and just kind of solidify what these notes were about. And I will see you then.